Here I'm going to introduce you to a nice visual tool in dealing with probability called a Venn diagram. And once you sort of have this Venn diagram created, then all the questions that I'm going to be asking below actually are really easy, because it just amounts to looking at your picture and interpreting. So this is just an exercise in using Venn diagrams. Usually the scenarios aren't quite so abstract, but I think this will serve a good purpose nevertheless. So here we have that A and B are events in a sample space S such that the probability of A is 0.6, the probability of B is 0.5, and the probability of A and B is 0.3. And we're asked to draw a Venn diagram, show the overlapping sets of A and B, and fill in the probabilities of the four regions formed. So the first thing you want to do when you make a Venn diagram is make your sample space a big rectangle. And again, remember, the sample space represents all that can possibly happen. So everything in here, all the probabilities that end up being inside this box have to sum up to the number 1. So let's let this red circle be the event A. Let's let the white circle be the event B. Now you overlap them to account for the possibility that there are events that are in both A and B, and then given the situation we know that's true because probability of A and B is 0.3. Now here's where you got to be a little bit careful or thoughtful about filling in the probabilities. They told us that the probability of A is 0.6 and the probability of B is 0.5. Well, what that means is that everything in the red circle has to sum up to 0.6 and everything in the white circle has to sum up to 0.5. Since there are two regions in each of those, right? There's the overlapped region and the one that's not overlapped. We kind of we don't really know exactly where to put the 0.6 and the 0.5. In other words, we can't put those in the circles yet. The first thing you really want to do is put in the value of the probability of A and B. That goes in this overlapped region here. So the probability of A and B is 0.3. So I'm going to put a 0.3 right there in the middle. Now is when you can move on to the probability of A. The probability of A is 0.6, which means that the region that's not shared by A and B has to be 0.3, so now that everything in the red circle sums up to 0.6. And that also means that in the white, the region that's not shared by the two would have to be a 0.2, so that everything in the white sums to 0.5. And keeping in mind that everything in the sample space, so we'll call this big sample space S, everything in there has to sum to 1, we know then that 0.3 plus 0.3 is 0.6 plus 0.2 is 0.8. That means that everything on the outside of both circles, the events that are in neither A nor B, is 0.2. Now we really did most of the hard work. We can answer these questions pretty quickly now. So for B, the probability that A occurs but not B, B does not, that just means we're looking at the region that's inside of A and is not inside of B. And that is the region that I'm underlining here in green, which is 0.3. For C, it says find the probability that B occurs but A does not. Well, that's just the region that's in B but not A, so that's 0.2. The probability that neither A nor B occurs, well, that's the probability represented by the region that's in neither circles, the region that's not contained in either circle. So that's this 0.2 here. It's not in A and it's not in B. Now E and F are where we have to do a little bit of work actually. The probability of A given B, and I mentioned before, or I introduced conditional probability before. This problem here, the probability of A given B, means that we know that B happened. And once you know that an event happens, that has the effect of shrinking your sample space. So now what we need to consider for the probability of A given B, the probability of A given B, represented like this, A given B, is just the probability of A and B divided by not the entire sample space, just the probability of B. Since we know that B happened, that becomes our universe. So the probability of A and B, the region that's shared by both, is 0.3, and the probability of just B is 0.5. And so the probability of A given B is 0.3 divided by 0.5. You can move both decimal places over 1 and just get 3/5 or 0.6 if you like. So there's a probability of A given B. Again, remember, since you're given B, you know that B happened, so that becomes that 0.5 is now the denominator of your fraction. And find the probability of B given A. Again, the probability of B given A is the probability of A and B happening divided by, and actually, if this confuses you, we could just say, in terms of the structure of the formula, I could say B and A to keep it, to keep it consistent with the sort of structure I used above. But notice B and A are the same. So either way you think about it, divided by the probability of A, since we know that A happened. So the probability of B and A again is 0.3 divided by, and the probability of just A is 0.6. And so this all reduces to, just going to shrink this a little bit. This reduces to, moving the decimal over, you just get 3/6 or 0.5. Alright, so your Venn diagram really makes interpreting the answers pretty easy, especially the first three. So taking care to set up a good Venn diagram is very important.